So I'm going to give a little review of the problem and the measurements that we made, and then I'll describe why I think magnetic reconnection at the base of the corona is responsible, at least in part, for the acceleration of the solar wind, or the initial energization of the solar wind. It's not an exclusive. There are other ideas, waves, Alfvén waves in particular. I'm not excluding them, but I'll tell you why I think reconnection is important. Okay, so first off, there's no QED in this talk. I have a good story about QED, about my training in QED as a PhD student and why I decided to be an experimentalist. It's mostly non-relativistic, apart from, and most of the solar wind kind of physics is largely non-relativistic, apart from some radio emission processes, what's called the semi-relativistic approximation that couples the perpendicular and parallel velocities. The solar wind, at least as we measure it, is about 95% protons. It's fully ionized, essentially, roughly 5% alphas, and then a small fraction. Obviously, it's 5% minus delta, and the little delta are heavies, so mostly higher ionization states of iron and oxygen. Plasma beta is from around 0.1 to 10, depending on where you are in the heliosphere, what the densities and field strengths are. In the inner heliosphere, what we're talking about here, it'll be less than 1 typically, but not a lot less than 1. The Alfvén Mach numbers are around 5 or less than 5, and you'll see that we go into sub-Alfvénic wind now with the Parker Solar Probe mission. And then when you get into the outer heliosphere and the wind speed stabilizes and the densities fall off, you can have Mach numbers of 10 or 20 or something. The distribution functions that we see are largely a core and a beam, so they're, as I said, protons and alphas mostly. And so there's a core distribution, which is typically a bi-Maxwellian, so there are large pressure anisotropies, at least in the inner heliosphere, and an alpha particle population that's similarly actually typically more anisotropic, and then beams that are densities of maybe 5 or 10% with respect to both the protons and alphas that are streaming limited, right? So they stream at speeds up to the local Alfvén speed, at which point they excite instabilities and relax. T-perp is typically larger than T-parallel in the inner heliosphere in the fast solar wind, which I'll define here in a few minutes. And this is part of the ion cyclotron heating problem. The electrons are typically cold, so there's a cold core, which is most of the density, and a power law that we call the strahl, which is sort of has characteristic energies from 100 to 100 eV to a keV or so. And then at higher altitudes, there's also a halo, which is thought to be the pitch angle scattered strahl. The scattering mechanisms are still TBD. And we are sort of trans-collisional, right? So in the fast wind, we see that we're collisionless, but there are times in the slow wind or in current sheets or things when we become collisional. And the way we measure that is by some fiducial collision rate times a transit time. Okay, so the problem is this. The wind, okay, so we see, this is more the morphology. So we see, typically what we see is fast wind and slow wind. The fast wind is thought to emerge from coronal holes, which are open field structures. At solar minimum, which is what this cartoon is trying to show, imagine a dipole, right? So the field over the poles is open. So it's the wind in the polar regions is fast. And wind that emerges from the equatorial plane, from the ecliptic plane, or near the ecliptic plane, is slow. And this is just a man-made construct, right? It's a few hundred kilometers per second is slow, and up to 1,000 kilometers per second is fast. And this really reflects, in the case of the fast wind, this reflects the kind of expansion of the field lines. The field lines can more or less expand radially out from the poles, and that gives a particular wind speed. But if they have to overexpand, then you lose the directed radial kinetic energy to some tangential energy or kinetic energy, and that slows it down. It's also the case that the slow wind is denser and it's richer in heavies, and that's thought to be due to the fact that it emerges in part from closed loop structures, and those closed loop structures spend more time heating and ionizing the neutral materials. Okay, so the problem is about energization and acceleration of the wind. So there's, of course, a big gravitational field. The escape speed of the sun near the surface is close to 700 kilometers per second or so, which you see is greater than some of the wind speed that we observe. And so you have to energize the wind at the base somehow to get it kick it out of the gravitational field. And most of the ideas about this are partitioned into kind of waves and turbulence or reconnection and shocks. Okay, so the scenario for waves is that you have some convective motion in the photosphere, and that wiggles around the foot points of the open magnetic fields, and launches alphane waves or some kind of wave, fast magnetosonic waves, and they damp and provide energy. And the reconnection is typically interchange reconnection is between closed loop structures and open fields. And that's what I'm going to argue that we have evidence of. Okay, so the simple model of the solar wind is Parker's model, right? So this is just a hydrodynamic fluid, it's isothermal. This is basically like Bondi accretion, but with the clock running backwards. So that's the Bondi curve. The Parker curve is this one, goes through the critical point. There's zero angular momentum. And of course, it's not realistic, right? It's isothermal. And so it just evades the need for heating, for extended heating as you go out into the wind. And it requires energy deposition below the critical point, which is here, which is typically for a solar wind-like parameter, should be at around 5 solar radii or something like that. Okay, so this is a model. It's very old, but it's still, it's unmagnetized, zero angular momentum, so it's pretty primitive, but it's still more or less, you'll see, seems to work at some level. Okay, the solar wind was discovered after Parker wrote his paper in '58. It was measured for the first time by the the Soviet Luna spacecraft at 1AU, and then following that by the Mariner 2 spacecraft at 1AU again. So they saw a directed cold beam, sort of KeV beam of protons radially emerging from the wind. And it's measured as in the white light with coronagraph instruments. So if you block out the disk of the sun and look for the fine structure in the wind, the white light structure, which is just Thomson scattered light off of density streams, you see it accelerating as it moves outward. And it's also been measured by Doppler shifted UV measurements of minor ions. Okay, so the way we measure it is with the NASA Parker Solar Probe spacecraft. So this is a big spacecraft. Well, I could put my arms around the base of it here. This is the spacecraft at the bottom. It's about as tall as me, and I can almost put my arms around it. There's a heat shield on the front. The heat shield, so we're going in close to the sun. I'll show you the orbit in a minute. We go into about 10 solar radii, and so at 10 solar radii, there's about a megawatt of thermal energy on the front of the spacecraft, and it is heated to, let's say, 1500 C or so at perihelion. So this front of it is a big ceramic faceplate, basically. It's a kind of technical ceramic called alumina, and it's sitting in a carbon cup, a carbon fiber cup with carbon aerogel behind it. And then there's some radiators here, which you can maybe not see. And we extend some instruments out into the full sun. These are antennas that we built at Berkeley, which are made of a reactor-grade niobium alloy called C103. And we extend some things in the shadow behind it, too, which have to be heated. It's cold enough back here that you have to heat magnetometers. And the spacecraft was launched in 2018. I want to say it's really a heroic work of thermal engineering, right? It's really extraordinary to have such a huge thermal gradients across the thing. The payload, which is down here in the spacecraft, typically operates, between plus or minus 40 C, which is, more or less kind of room temperature stuff. Whereas you have these huge, about 1500 C at the base and minus 100 in the shadow behind. This is a picture of it at Astrotech, and this is a picture of it in a big vacuum chamber at Goddard, and here it is on the fairing of the Delta IV Heavy. So we launched it in 2018, August of 2018, and right now we're here, so we're over. We're done in some sense. Our prime mission ended now, and we're moving into an extended mission, we hope. There's, of course, extraordinary uncertainty with respect to NASA funding. But the orbit is such that we go from, well, these are in the wrong units, but we have perihelion first we had a sequence at 35 solar radii, then we have a Venus encounter, and we use Venus to slow down to change the angular momentum of the spacecraft, then at 27, then at 20, 15, 13, 11.3, and as of Christmas Eve of last year, 9.8 solar radii. So this is the final perihelion altitude, or distance, and we'll stay now at this distance through the extended mission. And importantly, we launched in solar minimum. Solar minimum was in 2019, and we're now approaching solar maximum. And the goal is to go, which is complicated. The solar wind is very complicated and not ambient at solar maximum. And we'd like to go back to solar minimum at least and see the solar wind up close at solar minimum. So there are a couple of extraordinary things about this. One is the distance, and the other is the speed. When we're at this perihelion altitude, the spacecraft speed itself is around 200 kilometers per second. That's the Keplerian speed at perihelion, which makes it the fastest human-made object ever. And it also means that the solar wind at those altitudes is aberrated in at 45 degrees or so, because we're moving so fast. So what else is cool about the orbit? Another cool thing about the orbit is that we go prograde. right? So we start out retrograde, moving retrograde, and then we have a period, these are the families of orbits. The one we're in now is the last one here, 22 through 24. And then we have a period where, so the sun is rotating once a month or so, and so we have a period where we're essentially going radially into the sun and staying in one stream radially, and then we go prograde, and we cut through a lot of longitude here in a very short time. So typically about 180 degrees in just a few days, right? So we're slicing through solar wind structure at different speeds, basically. So a fixed structure in the solar wind will appear to have different durations in time because of this orbit, which has made it really, really useful for diagnosing spatial structure. Okay, so one of the things that we found is that we can use a really simple model of the magnetic field, what's called a potential field source surface model. So this is a current-free model, it's a potential model, so there are no currents in it, it's steady state. And what you do in a PFSS, what we call PFSS model, is you fix the magnetic field between two concentric spheres. The inner sphere, the boundary condition is a magnetogram measurement, so these are UV, typically iron or calcium line measurements that you can use to construct a vector magnetic field at the highest density point of the line of sight, so that's typically at the photosphere or the chromosphere. So you have a magnetic field measurement there, and then you put an outer sphere around it at some distance, which the notional number is 2.5 solar radii. And at that point, you insist that the magnetic field is radial everywhere, right? So it doesn't even have to be a sphere, but the sphere, obviously, if you use a sphere, it's a simple spherical harmonic expansion to solve it. And then you construct a field that's radial at that point. So what you're saying is that that's the point at which the wind escapes. Things below that, you can have closed loops, discrete structures. And beyond that, it's all escaping wind. And that gives you a solution, and then you can take that solution at the surface and propagate it out to some distance, the distance of Parker Solar Probe, for example. The flux conservation says that it should fall off like 1 over r squared, and compare it to your measurements. And when we do that, actually, let me go ahead one to show you that it works. It looks like this. So this is, actually, this is not the slide I want to show. That's the larger picture. This is the slide I want to show you. So these are expansions. The bottom, below this altitude, this is altitude versus longitude. This is the Parker Solar Probe orbit above, so it does its little radial dip and then back out. Actually, it starts here in the center, goes down, dips around, and comes back out. These lines are colored for the measured polarity of the magnetic field at Parker Solar Probe. Red is outward, blue is inward. And they're traced back down to that altitude of that outer sphere, this what's called the source surface. And below that, you see the model. You see the steady state model that's based on the magnetogram measurements. And so there are times when it works well, like that. You can see that the model predicts expansion of the wind out to here, radial outward, and that's what we see. And there are times when it doesn't work so well, for example, these loops. But if you lower the altitude of the source surface, you can clip open those loops. And so the source surface is not a sphere. It has some structure to it, obviously. But it largely works. And then you can take these measurements and compare them. So this is the Parker Solar Probe orbit. The field lines here are colored for the measured polarity, again, at Parker Solar Probe. And you can propagate that out to 1 AU. These are measurements from 1 AU, and you see that they largely agree at 1 AU too. So we think that we could have a reasonably good model, or we can use a really simple model, I should say, to say where the solar wind comes from on the, let me go back to this one, on the source surface, on this surface, and then using the model, the steady state potential model, trace those field lines back down to the photosphere and say, where did that bit of solar wind emerge from on the photosphere and the chromosphere? And if we do that, we can do something like this. This was our first encounter of Parker Solar Probe. So what you're seeing is the radial magnetic field as we go through perihelion. So it has a roughly 1 over r squared scaling, which it doesn't hold later, and that's a whole separate talk. And all of this structure these are Alfvén waves. These are fully steepened Alfvén waves. Delta B over B of 1, that's a whole other talk as well. They're spherically polarized, so they're almost completely incompressible, and the tip of the vector moves around on a sphere. Delta B is order of 1, so it's a really interesting problem. That's the Alfvén wave structure of the wind, but we can take this model and trace the field lines back down. So this is the Parker Solar Probe trajectory on a coronal image, and we come in like this during this perihelion and loop back out. And the little blue lines that you see here are tracing the origin of the magnetic field down to the corona. And what we see is, as we might expect, that this wind is emerging from a very small coronal hole. Okay, so we've done this now. We've got it down to an art, and we can say more or less where the wind emerges from on the photosphere. Okay, so this is the kind of the money plot. This is what we started to see on encounter 10. So this is about, goes down to around 13 solar radii or so. So this is a time series. This is what our data mostly looks like. And this black curve here is the radial speed of the wind, okay? And we're at perihelion somewhere in here, I guess. So what we see are these structures in the wind, what we've come to call microstreams. And here you see they're getting shorter in duration as we go through perihelion. And that is simply the fact that we're moving through them faster, right? So there are these stream structures that are emerging from the wind, all within an open coronal hole feature. And so the bottom plot here is the foot point longitude. So this is all mostly one coronal hole. Then we skip to another coronal hole, then to another coronal hole. And within that coronal hole, you see these stream structures. And so what is this? And I should say the alpha particle abundance is modulated within these streams too. That's the blue curve. And the alpha particle abundance is set very, very low in the corona, right above the chromosphere, where the temperature, you have to fully ionize the helium, you need to have temperatures of 50, 55, 60 EV or so. So it's very hot. So it's very right down at the base. And it doesn't change as it propagates out. So this tells us that the stream structure has its origins right at the source of the wind. If we take our measurements now, so these are the foot points from that encounter through these two coronal hole structures. So we're in this coronal hole, moving here, the magnetic field foot points. And then we jump to this coronal hole, and we move around a little bit in there. If we take these and zoom in a way with the model, with the PFSS model, we can see and drop the wind measurements on top of it. We can see that we have these modulations in the wind speed, which are on the order of a few degrees, 5 degrees to 10 degrees or so. And below them, and the foot points below them, are polarity modulations in the magnetic field, red outward, blue inward. So this is the altitude. Magnetic field is a function of altitude from the model, and we're crossing over inverted polarity magnetic field structure that has the same spatial scale as the streams, the wind streams that we're measuring. And this is now what we see really in every encounter. How am I doing on time? Doing okay, I guess. So these are several orbits. This is just to show you that if you plot the spacecraft trajectory on the Carrington plane, you see long duration. This is proton T-perp, but it's a proxy for wind speed. You see long duration streams that are basically when you're traveling radially, and you see shorter duration streams when you're slicing across them. So we're fairly certain, now we've done some statistics on this, we're certain that what we're seeing is 5 to 10 degree structure in the wind. And what is that? This is a scale associated with what's called supergranulation, which is a kind of rotating Rayleigh-Benard convection scale in the convection region of the sun. And you see it everywhere. So this is a map of the sun in magnetogram measurements. And all these structures are sort of 5 to 10 degree structures and polarity inversions. And the model is essentially this, that you have, this is the coronal hole feature. So this is an open coronal hole. These streams within, so you have this scale, which is called supergranulation, which is around 30 megameters, maybe 5 to 10 degrees. And associated with that convection scale, magnetic field is dragged either downward or out of the convection zone. And so you have accumulations of magnetic field, what are called network magnetic lanes, within these coronal holes, actually everywhere in the sun, that are associated with this convection motion, the supergranulation scale. And so this is all, in this case, a positive polarity magnetic coronal hole. So all the bulk magnetic field is generally outward here. On the edges, you have some cells that are closed. So these field lines will go back to the sun somewhere. So these are not sources of fast solar wind. But when smaller scale, granulation scale cells emerge from between these supergranules, you have a geometry which is favorable to interchange reconnection. So there's a reconnection between open field and closed loops here, and we believe that this is the source of the sort of jets that drive the solar wind. This is great. I made this last night on AI. So this is kind of my, using some AI thing that Berkeley provides. So this is kind of my image of it. The coronal hole has a bunch of little cells in it, and within these cells you see the streams of. So in this case, each shower head would be like a coronal hole, and within it you have all these little microstreams. And these are the source of the fast wind. Okay, so we've done some simulations. Actually, Jim Drake has done these simulations. We take our measured magnetic fields and our measured wind speeds, and Jim and Mark Swizdak initiate a reconnection geometry. So there's a closed loop on the left side here and an open field line here, and what you get is jetting. This is a really simple simulation, but it does produce power law spectra. And we make the argument that there's a reconnection time scale, which is essentially the spatial scale of the magnetic field divided by a reconnection rate. And there's a travel time out to Parker Solar Probe, so it's the distance to the spacecraft divided by the wind time. And these two things have to be essentially comparable to one another. And that gives us a handle on the reconnection rate. If they were very different from one another, then Parker would pass individual streams and there would be nothing between them. If the reconnection time scale was a lot larger than the travel time scale, and if it were the other way around, the flow would be relatively uniform. So the argument is that they're comparable, and that gives us a reconnection speed, an inflow speed of around 3 kilometers per second, which gives us gives us an energy per particle, which provides an Alfvén speed of around 350 kilometers per second, which is consistent with measurements. So these plots on the left are energy spectra from Jim and Mark's simulation with power law tails on them. So this is the proton spectrum. This is the alpha particle spectrum. And on the right are measurements at Parker Solar Probe. So this is protons. We have a big energy gap, but these are triple coincidence measurements, so they're very reliable measurements with real error bars on them. So that the power law tail of the protons is comparable to the simulation, and the alpha is, okay, we don't have enough points up here, but and I should say subsequently on the latest encounters, which are now at 10 solar radii, we're really filling this in. And we also have the heavier ions too, the iron and oxygen ions to throw into the simulation. So that's the argument. So what we see, this is a bunch of several orbits of data plotted on top of so that's wind speed, that's radius, and these are Parker wind solutions here. So the lower bound is basically the simple Parker wind. You have to modify a little bit to have a polytropic index at higher altitudes. And the wind speed seems to be bounded from below by the Parker model. So if you liberate some plasma and get it out of the gravitational well, you'll have at least a Parker wind. If you provide more energy in a sort of stream structure, it can surpass that. Okay, and then finally, I just want to show you the measurements from the second to last encounter, which was at 9.86 solar radii. So this was so this is the orbit of Parker here. And we had at that time other spacecraft available too. So there's this European Solar Orbiter spacecraft. So here's Parker's perihelion encounter in an inertial system. There's the Solar Orbiter spacecraft from Europe. And out here, our spacecraft, that's 1AU. So there's a spacecraft at 1AU at Earth and stereo. And what we saw in this last encounter was extremely fast wind. Now we're getting to solar maximum, so essentially the dipole is rolling over, right? And it'll reverse polarity. It's not a simple rolling over. It's a complicated rolling over, but we're looking down the throat of the dipole now more. And what we see is this is the last good encounter. So this is the Mach number at the top here. So we go where it goes red is subalfanic. So this is all subalfanic flow. It's very low density. So this is the density normalized to 1AU values. So the R squared term is removed here. This is the magnetic field with the R squared removed as well. And so there again are the switchbacks. And we see these really discrete microstreams that get to be, it's just crystal clear now with the winds accelerated within them. And another curiosity here is that the magnetic field, the Alfvén waves, seem to be organized by these switchbacks or by the microstreams as well. It's not clear if that indicates that the Alfvén waves have their origin at the source with the enhanced wind, or whether they're created by shearing, stream shearing on the way out, or phase mixing or something. There are several different ideas about that at the moment. Okay, and then this is again that stream. So what we're looking at, this is Carrington longitude in the solar frame. And this is the wind speed here. And so this black curve is the Parker Solar Probe speed, a wind speed at about 500 kilometers per second. The blue curve is Solar Orbiter, which is at 60 solar radii. And the red is the wind spacecraft at 1AU. And so we can actually see an individual stream being energized as it goes out. And this is that data plotted. That's Parker Solar Probe, Solar Orbiter, and wind. And these are now colored. These stream structures are colored for the speed at Parker Solar Probe. And so we see discrete streams that merge all the way out to 1AU. And we can watch the wind being accelerated. This is that coronal hole. So this is a passage right through the center of relatively large coronal hole, which is in the Carrington ecliptic. And then I just want to show this last plot. I think this is my last plot. So this is that data again. So these are all of our previous orbits. Great, perfect. All of our previous encounters, all the dots here showing the kind of, again, that underlying Parker solar wind model, and then the streams on top of it. And this is out at further distances. And so this can all be kind of put together into a model. This is a completely separate talk, but the thermodynamics of the expansion of the wind are consistent with the magnetic energy. The missing heating that makes it behave approximately isothermal is provided by the magnetic energy budget. So somehow those Alfvén waves, those highly steepened Alfvén waves, which are not really good at heating, obviously, you have to cascade it down into something kinetic or cyclotron waves or some stochastic fluctuations, but somehow that energy, the magnetic field energy of the Alfvén waves, is what's providing that isothermal type behavior. And this is that last encounter that I just showed you, which is the most extreme that we've seen to date. I think that's it. Okay, so summary. So the wind in the inner heliosphere is relatively coherent, and it's structured on these microstream scales, which are associated with supergranulation, or the same scales as supergranulation. The large amplitude Alfvén waves, which have been, there's a term of art here, they're called switchbacks, are ubiquitous and they're modulated by this network scale, this supergranulation scale. The alpha particle abundance is also modulated by this scale, and that's, of course, and I didn't talk about it, but the energy of the superthermal tail of electrons is as well, and these are things that are known to be frozen in very deep in the corona at the source, essentially. There are ion tails out to a couple hundred keV that are consistent with interchange reconnection simulations. This is the thing I just talked about, and then the extended heating mechanism is, we believe, Alfvén waves. So the proposed interpretation is simply that reconnection at the base of the corona within coronal holes provides the energy to liberate the solar wind. This is these are known values of the energy, and our reconnection simulations are consistent with the energy, the work that's required to accelerate the solar wind. And so that's the proposal. I think that's my last slide. Yep.
Thank you for a very nice talk. Any questions? Yeah, there's one at the end.
Thanks, Roger. Thank you, very cool. Maybe I was wondering if you could give a bit more details about what you just mentioned on electrons. So what I was wondering is, do the electrons you get in your simulation match the expectations we have from other observations, and is that electron dynamics important to have your protons match the PSP observations?
I mean, it's an interesting question that we haven't really plumbed into sufficiently. I mean, the straw that you're seeing, the superthermal tail, is thought to be the wind, due to the source, right, at the origin. We don't see it as modulated. We haven't seen any modulated structure apart from a little lower temperature within the supergranulation scales. But there's no clear way to trace it back, which is maybe sensible. And then the core, the cold population that we see are just trapped electrons, right? There's an ambipolar electric field. There has to be an ambipolar electric field, and that traps a population of electrons that are cold and well, it's almost collisional sometimes. But we haven't really, I think in part because the measurements are more difficult to interpret and they're less structured, we haven't really tried to do anything serious with that yet. It's a good question, though. You can see evidence of the ambipolar field in the backward part of the electron population. The superthermal part is stripped off, and that's because it's trapped. And so we do see evidence of the ambipolar field. Hi, Roger.
Well, congratulations. There's a lot, see it's all come together. The switchbacks,
yeah.
Do they require something like an interchange instability happening on the solar surface, or do you think they could also appear in something like the magnetoturbulence simulations we saw early this morning?
There are a lot of different, strident ideas about it, frankly. I sort of side with the idea that these are due to stream-stream interactions. We have velocity shear at the boundary of the streams, and we're generating Alfvén waves there, or perhaps phase mixing within the streams. But the jury's out on that. I mean, we know that there is wave motion, of course, down at the base of the corona. If you look at remote sensing measurements, you can see wave motion, although it's generally quite large scale compared to these things. These are, you know, at the spacecraft altitude, they're a second. The switch around can occur in 1 second or so.
Is it an experiment?
Yes, potentially, yeah.
Well, a related question, is there a power spectrum of the switchbacks? Know the scale over which?
There's no particular scale. If you make a distribution of the kind of the time scales, there's no particular scale. I mean, there's a largest scale, which is essentially the stream structure scale, but they go down to, you know, fractions of a second. And they're really alphanic, right? They're incompressible, and the wind speed flips around too, which is where the name switchback came from, because when the radial field goes outward, the velocity can go inward.
But then can you get a power spectrum?
Oh, yes, if you just, yes, a power spectrum. Yeah, if you just take a power spectrum, it's, you know, Kolmogorov-like. It depends on the direction you're looking with respect to the field, and of course at the sort of ion scales, it steepens, and there's an electric field component. It evolves to kinetic Alfvén waves, basically. And there are ion cyclotron features near the convected gyro periods.
Sure, but I was talking about the switchbacks.
Yeah, the switchbacks are basically kind of a Kolmogorov-like or Goldreich-Schrieder kind of spectrum.
So is there a blending between the two then?
Between the two?
Well, you have the small scale, kinetic scale.
Yeah,
right?
yeah.
Is there a blending between those and the power and the switchback?
I mean, it's a spectrum that breaks at around the ion gyro scale or so and flattens.
So it's the same phenomenon.
It's the same phenomena. Yeah, yeah. It's just that it's and you might expect, of course, that it's nonlinear, but I mean, it's very nonlinear, right? Yeah.
I've got a question. Right here. Right here.
Oh, sorry.
Hi. Hey. You said the switchbacks are alphanic. Do you mean that they actually follow an Alfvén mode wave dispersion relation, or do you just mean that they have their delta B and delta B in the right direction?
They have the first motion of an Alfvén wave eigenmode, right? Basically, but they're so nonlinear that they're not really.
Okay.
Yeah.
And when you take a spectrum of them, I mean, they're kind of non-local in K-space, aren't they? So one switchback could go everywhere in K-space.
Yes.
So I don't understand what
that's right.
Kolmogorov means necessarily.
If you take a spectrum of them, like I said, you get something that is, Goldreich-Schrieder-like, right? And so it's 5/3 in the perpendicular direction, basically. And so, but yeah, it's non-local in K-space for sure.
Okay, thanks.
Yeah.
Beautiful, beautiful results. You showed very concrete evidence that there are discrete reconnection happening close on the surface, right? But that doesn't give you the final speed of the wind.
No,
there is extra acceleration that happens up further out.
That's right.
Is that pressure acceleration, or and if so, is there heating by waves, or is that heating by another reconnection? How do you see the further?
So what we can say at the moment is that the magnetic energy in the switchbacks compensates for the heating, the missing heating, right? So if you take like an isothermal or a polytropic kind of equation of state, you need extra heat, you need extra energy or pressure in there to keep the wind fast, and the magnetic energy associated with the Alfvén waves, the Alfvénic switchbacks, is sufficient to do that.
But you don't see discrete reconnection. It's just some kind of volumetric dissipation.
That's right. That's right. It's some kind of volumetric dissipation. We see discrete reconnection events within the heliospheric current sheet, where the polarity inversion occurs near the equatorial plane. We see huge reconnection, just large scale, very anomalously large scale, but but not within these events. No.
Any more questions?
Two quick questions. So one, do I see it right that there is some heating beyond what you would call an Alfvénic surface of the solar wind?
Yeah. The heating is extended. It continues beyond the Alfvén surface for sure.
So what could cause that?
I think, again, it's the Alfvén waves.
Okay.
I think it continues, the Alfvén wave heating has to continue out to where this curve flattens, which is, beyond 60 solar radii. And then, the Alfvénic fluctuations, these switchbacks, this is a whole another talk, which would be great to give, they start out as very incompressible, right? In the inner heliosphere, the magnetic field modulus is just flat, right? But as you get out to maybe 0.3 or 0.4 AU, it starts to become compressible, right? And so there's some evolution to compressibility, in the compressibility as we go outward, which I think is probably one of the clues.
And the second quick question is, so should I think of this interchange reconnection as also plausible events to inject electron beams for radio bursts?
I would think so. I would think so. We just don't see, the electrons are just like fully dispersed. The superthermals are kind of fully dispersed when you get out to these altitudes, you know, and they're non-local too, right? I mean, there's a backward population which has come from, you know.
But you don't know whether the solar bursts come from the same field lines as, you know, you would expect, you know, eventually connecting to the
we don't really see
events.
We don't really see beams apart from beams that are associated with flares, which are really clear in the measurements. We don't see little beams associated with, or beamlets associated with the streams. I look for them every time after every encounter. I try to de-disperse the superthermal electrons, but I've never seen anything.
More questions? Okay.
Oh, there's one more.
Thanks for a really nice talk. What's the main goal of the extended mission going to be?
The extended mission will be, the goal is to go down, so at the, I don't need to show the slide again. So we began at 35 solar radii altitude, and none of this structure is obvious there, right? And now as we've gone into solar maximum, deep into the mission, we're at solar maximum. So every perihelion, you know, you see these stream structures, but you also see CMEs, you know, large disturbances. You see the effect of active regions, you know, really enhanced magnetic fields, which have low density associated with them. So the wind is very complicated. You have to like take little slices. And what we really like to see is, you know, the kind of the virgin solar wind again at solar minimum at 10 solar radii. And it's also, you know, it's a $1.4 billion project. We don't want to turn it off yet. I mean, you know, it's orbital dynamics, so as long as it stays pointed at the sun, it'll just keep orbiting. But eventually what will happen is it will run out of station-keeping propellant, I suppose, or there'll be some failure, some hardware failure, and it'll off-point at some point where it's too close. We off-point it when we're beyond the orbit of Venus for comms sometimes. It has a kind of a fixed or two-axis gimbaled radio communication thing on the back of it, so we have to point it at Earth. But we don't ever off-point it within the orbit of Venus, and that's what will happen eventually when it runs out of fuel or something. It'll tip on its side and burn up.
Okay. I think we should thank our speaker.
Thanks.